Hello, in this video we're going to talk about contingency tables. A contingency table, or two-way frequency table, consists of frequency counts of categorical data corresponding to two different variables. One variable is used to categorize the rows, and a second variable is used to categorize the columns. What we're going to be doing is doing a test for independence. We want to test the null hypothesis that in a contingency table, the row and column variables are independent. That is, there is no dependency between the row variables and the column variables. This is very similar to what we did with the goodness of fit. The notation is also similar. Capital O is going to represent our observed frequencies. E is going to be our expected frequencies. R is the number of rows in your contingency table, and C is the number of columns in your contingency table. The null hypothesis will always be that the row and column variables are independent, and the alternative hypothesis is always going to be that the row and column variables are dependent. The test statistic is the same as it was for goodness of fit. Chi-squared equals the sum of the observed minus the expected squared divided by the expected. This is always a right-tailed test, and the degrees of freedom for this one is r minus 1 times c minus 1. So this test statistic can be calculated by hand. It is quite a long and tedious process to calculate it, however. For each one of the values in the table, you would have to calculate E, and E is the row total times the column total divided by the grand total. I will calculate a couple of these so that you can see how it's done in case you are needing to do it by hand. And if you need to do it by hand, then you would need to fill out that big table that we did in the first example of the goodness of fit test as well. So we'd had a column of the observed minus the expected, a column where the observed minus the expected was squared, and then the last column was the observed minus the expected divided by the squared, and then divided by the expected. And then you had to add up the last column in order to calculate your chi-squared statistic. So we will calculate a couple of these values. Let's just take a look at how we would calculate E for 54. So we would need to take our row total times our column total. The row total is 66, the column total is 182, and then you have to divide by your grand total. So I have the row totals filled in over here on the right, and I have the column totals filled in on the bottom, and then this is our grand total down here on the corner. So for this one, it would be 66 times 182 divided by 253. So if we put that into our calculator, we get 47.478. Now let's take a look at calculating the expected value for 51. So E is going to be 92 times 71 divided by 253. So for 51, we would need that row total, 92, the column total 71, and divide by the grand total. And when we do that, we get 25.81, and the 81 repeats. So that you would have to do that calculation for every single value in your table. Now, I would hope that most of you have a graphing calculator. If you have a graphing calculator, then you would do the following. So you're going to want to select matrix. This is second, and it's the button right below the math button. So it's second and then it's the button with x to the -1 on it. So that's the key that you want to push to go into the matrix area in your calculator. Then you want to right arrow over so that edit is highlighted and hit enter. And make sure that you put your table in matrix A. Then you'll need to enter in the number of rows. In this example it's 4, and the number of columns. In this example that will be 2. Enter the numbers in the contingency table into your matrix, and then you're going to want to go to Stat, Tests, and then select the chi-squared test. The observed values will be in the matrix that you entered above, so you should put that in matrix A. And then your calculator will automatically calculate the expected values and store them in matrix B. And then you want to highlight Calculate and press Enter. So when you do that for this example, it should give you a chi-squared statistic of 58.3933 and a p-value of 1.2955 e -12. So this -12 means move the decimal 12 positions to the left. So this p-value essentially is 0. The degrees of freedom, it's your rows minus 1, so that's 3, and then the columns minus 1, which is going to be 1. So 3 times 1 gives us 3 for our degrees of freedom. Whenever we're doing these, our null hypothesis is always going to be that the row and columns are independent, and the alternative hypothesis is always going to be that the row and columns are dependent. So with the information that we have a chi-squared statistic of 58.3933. So we have a p-value of 1.2955 e -12, so essentially 0. And so that's going to tell me to reject my null hypothesis. You should also make a graph for these problems. We're not given a alpha level with this. So, and I didn't talk about what this problem was about either. So this is a study of success with different treatments for stress fractures. And if someone had surgery, 54 of them were the treatment was successful, 12 of them the treatment was unsuccessful. If they had a weight-bearing cast, 41 of them were successful, 51 of them were not successful. A non-weight-bearing cast, 70 were successful and 3 were not. A non-weight-bearing cast less than 6 weeks, 17 were successful and 5 were not. So when we do our graph, and it doesn't tell us what the alpha level is, so we would assume that our alpha was 0.05. And we had a p-value that was 0. And remember, this is always a right-tailed test. And so our p-value is in the tail. Our p-value is smaller than our alpha, and so that's why we are rejecting the null. If, for whatever reason, you're going to be doing this calculation by hand, then you would also want to look up the critical value in your chi-squared table. We have 3 degrees of freedom, and we're doing a 0.05 level test. So bring up your chi-squared table. The area to the right is 0.05, and we have 3 degrees of freedom, so that gives us a critical value of 7.815. So if you're going to be using that, then instead of alpha here, we would have our critical value, and here instead of p-value, you would have your chi-squared statistic. And that was 58.3933. So now we need to write out our conclusion. We're rejecting the null hypothesis, and so that means that these are not independent, they're dependent. So our conclusion is going to be that there is sufficient evidence to reject the claim that the type of treatment is independent from the success or failure. And if we go back up and take a look at our table, we had, out of the people who had surgery, 54 were successful and only 12 failures. Weight-bearing cast, 41 success, 51 failures. Non-weight-bearing cast, 70 successes, 3 failures. And if you had your cast for only less than 6 weeks, it was 17 successes and only 5 failures. But it looks like from the data in our table that the non-weight-bearing cast was the most successful treatment. So basically what we're saying here is that the type of treatment that you had will have some effect on whether the treatment is a success or a failure. In example 2, the table below with row variables whether subject was given 4 quarters or a $1 bill, and a column variable whether the subject purchased gum or kept the money, we're going to use a 0.05 significance level to test the claim that the row variable is independent of the column variable. And what do the results of the test tell us? So first, our null hypothesis is that they're independent. And our alternative hypothesis is that they're dependent. Next, our degrees of freedom. That's the number of rows minus 1 times the number of columns minus 1. There are 2 rows and 2 columns. 2 minus 1 is 1, and so we just get 1 times 1, or 1 degree of freedom for this test. When you enter this matrix into your calculator and perform the chi-squared test on this, you should get a chi-squared statistic of 12.162 and a p-value of 4.877 e negative 4. So that's approximately 0. With a p-value that small, we're going to reject the null hypothesis. If you're doing this by hand or for whatever reason you want your critical value, you can look that up in your table. We have a significance level of 0.05 and we have 1 degree of freedom. So here is the 0.05, and 1 degree of freedom gives us a critical value of 3.841. So make a graph. Alpha is 0.05, and our p-value is approximately 0. And so that would be doing the p-value method. If you're going to do the critical value method, then this would be our critical value of 3.841, and this would be our chi-squared statistic of 12.162. Next, we need to make a statement for our conclusion. We're going to conclude that the row and the column variables are dependent. So we have sufficient evidence to reject our claim. So our conclusion statement is there is sufficient evidence to reject the claim that the decision to purchase gum or not is independent of getting 4 quarters versus a $1 bill. Then go look at our table, and if someone received quarters, 27 of them purchased gum versus 16 that kept the money. If they received a $1 bill, only 12 of them purchased the gum, while 34 kept the money. And so we can see that more of them purchased gum if they were given quarters. So they were more likely to purchase gum. Given 4 quarters. In the next example, a randomized controlled trial was designed to compare the effectiveness of splinting versus surgery in the treatment of carpal tunnel syndrome. Results are given in the table below. The results are based on evaluations made 1 year after the treatment. Use a 0.01 significance level to test the claim that the success is independent of the type of treatment. What do the results suggest about treating carpal tunnel syndrome? First are null and alternative. The null is that they're independent. The alternative is that they're dependent. And our degrees of freedom is, we have a 2 by 2, 2 rows, 2 columns. So subtract 1 from each of those and we get 1 times 1. And so the degrees of freedom for this one are 1. Entering all of this information into your calculator, you should get a chi-squared statistic of 9.750 and a p-value of 0.00179. And so this tells us that we're going to reject our null hypothesis. If you're using your table, then the critical value that you will get, we have a 0.01 significance level with 1 degree of freedom. So here is the column for 0.01. 1 degree of freedom gives us a critical value of 6.635. Making a graph, our alpha is 0.01 and our p-value is 0.00179. And so again, we're going to reject the null. If you're using the table with the chi-squared statistic, then critical value 6.635 and your chi-squared statistic would be here, and that was 9.750. Now we need to make a statement about our conclusion. So our conclusion is that there is sufficient evidence to reject the claim that the success is independent of the type of treatment. And if we go and look at our table, if you had a splint, 60 were successful versus 23 that were unsuccessful. If you had surgery, 67 were successful versus 6 that were unsuccessful. And so it looks like from our table that surgery was more successful. In our last example, a case control or retrospective study was conducted to investigate a relationship between the colors of helmets worn by motorcycle drivers and whether they are injured or killed in a crash. Results are given in the table below. Test the claim that the injuries are independent of helmet color. Should motorcycle drivers choose helmets with a particular color? If so, which color appears best? So the first row in this table gives us the number of people that were not injured. So if you had on a black helmet, 941 were not injured, 377 if you had on a white, yellow/orange was 31, red was 170, and blue 55. Injured or killed for black was 213, white 112, yellow or orange 8, red 70, and blue 26. So go ahead and enter this into your table. So there are 5 columns and 2 rows in the table. And our null hypothesis is that they're independent. Our alternative hypothesis is that they're dependent. When you enter this in, you will need degrees of freedom. There are 5 columns in our table and 2 rows. That would be 4 times 1. So we have 4 degrees of freedom. When you enter this into your calculator, you should get a chi-squared statistic of 9.971 and a p-value of 0.0409. The critical value, so we have 4 degrees of freedom. It doesn't state a significance level, so we'll assume a significance level of 0.05. Here's the row or the column in the table for 0.05, and we had 4 degrees of freedom, so that gives us a critical value of 9.488. Making a graph, alpha we're assuming is 0.05. Our p-value is 0.0409. Based on this, we will again reject the null hypothesis. If you're going to be doing the critical value way, then the critical value would be down here of 9.488, and this would be your chi-squared statistic of 9.971. Next, we need a statement about our conclusion. There is sufficient evidence to reject the claim that injuries are independent of helmet color. If we go ahead and look up at our table, then it's a little bit less clear as to which of these is more successful than the other one. But we could figure out a percentage, and so you would take 491 divided by the total number of people with a black helmet. And so if you do that, you would do 491 divided by the quantity 491 over 213. And so you could do that calculation for each number in your table. So 377 divided by 377 plus 112, and so on down your table. And I'll go ahead and fill in those percentages. So I've gone ahead and filled them in. If you had a black helmet on, you had a 70% chance that you were not going to be injured. White, 75%. Yellow/orange would be 79%. Red, 71%. And blue, 68%. So these are percentages that you will not be injured. And so we would want to choose the highest in this. And we can see that they're all fairly close, actually, but the highest would be the yellow-orange. And so this would be the color that you would maybe want to select. The other one that's fairly close is a white helmet at 75%. So that's it for this video. Let me know if you have any questions, and I hope you're having a great day.